cumbersome? Is it easier to carry it around? Yeah, nice and self-contained. Is it less vulnerable to dehydration? Yeah, we are not. There are some animals even better at this than we are. We don't have a lot of adaptations for reclaiming water as we exhale. Some animals do. But we certainly lose less water this way than we would with the other one. All right, is it more protected from infection? Absolutely. There's only one way in, and that way is well defended. We have lots of structures along there for filtering and capturing things that should not be in the air. So what's the cost? What is the disadvantage of this system? I can think of a couple of significant ones. One, if something blocks that passage, we die.
And it's right next to the esophagus.
Yeah, which seems like a weird design. We'll talk about that a little bit. That's not the case in every mammal. The other main problem is, in order to keep fresh air over that membrane, you've got to bring it in, which means that you have to breathe all the time. If you ever stop breathing for more than a few minutes in those circumstances, you will die. So we have areas of our brain devoted to nothing but causing us to breathe all the time. That's probably the main disadvantage, is that we have to breathe. Make sense? Of course, we get the sound for free. Since you've got air moving through this narrow passage, it's pretty easy to put in a couple of things to vibrate there, and now you can make noises. Questions there? Okay. So that explains why our respiratory system is arranged the way it is, as opposed to this. We get our exchange surface, we just have to keep it crumpled up. So let's talk for a moment about what's in this air, this stuff that we apparently have to move around. I don't know about you, but I kind of remember when I first realized there was something here. That, I don't know, yeah, one day just sitting there going, you feel something, there's something here. That's apparently air. So what's in the air? Air's a gas mixture. What gases? CO2, oxygen? What's the most common gas in air? Nitrogen. N2. Makes up about 78% of the air around us. What does nitrogen do for us? Nothing whatsoever. Nitrogen doesn't do a darn thing. More or less. Nitrogen has no beneficial effect on us. Now, under very high pressure, it can act as a narcotic. In this chapter, we talk some more about scuba diving. Anyone who's been trained as a diver knows about the idea of nitrogen narcosis, or rapture of the deeps, which makes people do especially stupid things when they're breathing high pressure air. Okay, what's the next most common gas? Oxygen, O2, at about 21%. Oxygen's kind of interesting stuff. The reason it's useful for us is because it is an extremely reactive gas. It's so reactive, in fact, that while there are natural sources of oxygen, non-biological processes that produce oxygen, for any significant amount of oxygen to be in the atmosphere of a planet, the only way we know of for that to happen, for large amounts of oxygen to show up, is through living things. To the point where exobiologists are pretty convinced that if we ever analyze the spectra of the atmospheres of other planets and find one with a lot of oxygen, it's a very good guess that there's living things there. Absolutely, which are living things. Yeah, their process of photosynthesis produces the oxygen that we use. You can get oxygen from some minerals too by non-biological processes, but it's so reactive that if all the life on Earth disappeared, so nothing's making or consuming the oxygen, it would end up reacting with stuff on the surface to the point where it would rapidly leave the atmosphere. So if we think that if we ever find another planet with a lot of oxygen in the atmosphere, it probably means there are things there that metabolize like we do. Kind of an interesting idea. It also is an interesting bit in the history of life. Almost certainly the first life on Earth was anaerobic. The earliest living things that similar to bacteria would have been anaerobic creatures because there wasn't really any significant amount of oxygen in the atmosphere. They didn't need it. In fact, it was toxic to them. It's so reactive that it's a poison. But as a waste product, some of them ended up producing oxygen. So oxygen starts to build up in the atmosphere. And we end up with a crisis when early life almost poisons itself to death by dumping its waste oxygen to the atmosphere so much that it builds up to the point where everything is dying from oxygen, until a few of them evolve the capacity to use oxygen. They evolve aerobic metabolism. And they start living on the toxic waste that everyone else is generating. And now we have a better system where some of them use it and some of them make it, and we end up with life kind of as we are now. In fact, probably that some of the descendants of those things that evolved that capability are living in you right now as mitochondria. Those were almost certainly independent organisms long ago. Pure oxygen has some problems. Oxygen under high pressure does become a poison effectively. It does damage the nervous system. People who do like commercial diving under super deep diving, they can't breathe normal air because the levels of oxygen in it are too high. They have to breathe special gas mixtures to produce oxygen. Yeah, I always thought so. Okay, other questions? All right, so 78% nitrogen, 21% oxygen, 1% other, yeah. And that other includes some noble gases, small amounts of neon, krypton, argon, some water vapor, and carbon dioxide. Interestingly, if you look at most textbooks, they list CO2 at 0.03%. The ones published now, doesn't seem like much, but it is a big deal. CO2 levels have not been at 0.04% probably for, I'm trying to think, our estimates, it's been, I think, millions of years since they've been as high as they are now. Yeah, folks, I'm sorry, but it's a problem. It's a serious, serious problem for many reasons. One of the main ones, remember what we said about CO2 in water forms an acid? Ocean acidification. As the CO2 dissolves in ocean water, the pH lowers slightly. Some of the single-celled organisms can't make proper shells under more acidic conditions, so they start dying, and they're responsible for part of the food chain and sometimes for oxygen production. It's a problem. Yeah. You have a question? No.
Okay, no, I was going to add on to that.
Okay, if there's something to add, feel free.
No, you got it.
All right.
Can't we fix it with more trees and stop cutting them?
There are things that can be done to fix it. In theory, in fact, vegetation is increasing in some areas on Earth because of this. The thing is, it'll take way too long for that. At the current rate at which we're producing CO2, even if we stopped producing very much of it, it's still going to build up for a while, and we would have trouble putting in enough plant life to actually absorb enough of it to seriously affect that.
And totally off topic, but along with what you're saying, a lot of people feel that just replanting trees for lots of trees, it's not the same at all, because old growth is dealing with far more than putting a little sapling in its place.
It would help, but that's not enough on its own. If people wanted to seriously combat this, it requires a complete change to the economy. You have to radically change what kind of stuff we do in terms of power production. You have to invest a lot in carbon capture technologies that specifically suck it out of the atmosphere. Personally, I am letting all the weeds in my lawn grow for this purpose. On the same theory. Say, look at all this biomass. These things are going to save the planet. That's not going to help. But it won't hurt anything, and I think it looks pretty that way.
Farming cattle for human consumption is the number one.
That is a big factor too. Yeah, it is true. There is significant evidence that vegetarian diet can help with this. I haven't gone there yet, I will admit.
No, but even a reduction makes.
Anything you can do will help. But the biggest problem is people don't believe it's a problem. It really, really is Please, please. Okay, anyway. Oh, there's still a lot. Anyway, but, set it aside. So, now, here's the thing about gases though. I can talk about percents of a gas, but when I want to know where the gas is going to go, I need to talk about pressures. And gases work very much like liquids in this, in that high pressure things go from high pressure to low pressure. One of the big differences is that gases can be compressed or expanded, which changes the pressure, but we'll get to that in a moment. Let's talk for a second here. Let's imagine we have two containers filled with gas mixture, and here we have a valve, which can be opened or closed. Over on this side, I have a gas mixture at a total pressure of 1,000 millimeters of mercury. Over here I have a gas mixture with a pressure of 1,000 millimeters of mercury. When I open this valve, is there any significant pressure difference?
No.
So will the gases be moving? They'll be moving, but they'll be moving equally and opposite. You won't open this and feel a breeze one way or the other. But what if I do this? Let's say this side is 50% oxygen and 50% nitrogen. This side is 100% nitrogen. If I open that valve, will the gases be moving?
Yes.
You just said they weren't. Will they be moving? What makes you say yes now but no before? It's not different. It's
Yeah. The weight of the gas.
the pressures are still the same. We're not worried about that right now. So I'm hassling you here because, to point out a problem. We say gases move by pressure differences. So if I just said it's equal, we say, well, then they're not equal and opposite. But now you're tempted to say, yeah, because of diffusion, right? I mean, this side's got oxygen, that side has no oxygen. Won't the oxygen diffuse? Yes, it will. But if we want to talk about oxygen moving from one side to the other, we have to talk about pressures. So people came up with a way to talk about these in terms of pressure, which is the idea of partial pressure. So we can say that we can talk about the partial pressure of oxygen in this area and the partial pressure of nitrogen, which is the proportion of the total pressure made up by each of those gases. And partial pressures are very easy. If this thing is a total pressure of 1,000 and it's 50% oxygen, then the partial pressure of oxygen is 50% of the total. So what's the partial pressure of oxygen in here? 500. So let's replace this 50% with 500, same for the nitrogen. So this is PO2 and PN2. Each of them has a partial pressure of 500 millimeters of mercury. What's the partial pressure of oxygen over here? Of oxygen? 0, yeah. So 0 is the PO2. How about nitrogen? There we go. Now I can look at each gas separately and talk about how each gas is going to move from high to low pressure. So oxygen has a pressure of 500 here, 0 there. Which way will oxygen be going?
Left to right.
Nitrogen is 1,000 here, 500 here. Which way will it be going?
Right to left.
They each have a delta P, a difference in pressure of 500, so equal flow. So here, you won't feel a breeze, but there will be oxygen and nitrogen moving overall in opposite directions. Effectively diffusion. Just since it's a gas, we're going to talk about pressure rather than concentration. Make sense? Are there questions about that? So partial pressure is pretty easy, right? Sure. Let's test it. The overall pressure in the atmosphere is about 760 millimeters of mercury at sea level on a typical day. It varies. Find me the partial pressures of nitrogen, oxygen, and CO2. Math. Very simple math, though. I see some people looking at me like, you do it, Dr. Red. Do it. You do it. Let me put it this way. You're going to have to do it in about 2 weeks. Might as well learn now. I want you to, if the overall pressure of the atmosphere is 760 millimeters of mercury, I want you to tell me the PN2, PO2, and PCO2 of the atmosphere. Partial pressures of each of those three gases.
593.
Okay, hold on. Don't tell me yet. I want to give people a chance to work on it. All right, somebody give me a PN2. 593. Does that rounded to the nearest whole number? That's fine. Does that match other people's? Okay, what about a PO2?
157 or 160. Yeah, 160.
That's about right. What about a PCO2?
8.
8?
Oh, CO2, I thought, I was doing other, sorry.
I'm looking for CO2.
Oh, my bad.
Wouldn't that be
0.3?
0.3? This one can be slightly tricky because when you're figuring out what to multiply when it's a fraction of a percent, sometimes gives people trouble. You're multiplying 760 not by 0.04, but by 0.0004,
Yeah, 0.3.
which means you get 2.3. Yeah, those look about right. So, I could say, for example, that if I have a bottle of gases, and the PN2 in here is 500, and the PO2 is 200, and the PCO2 is 60. And I pop the top on that bottle. Total pressure, 760. So I pop the top and it doesn't go or it just goes. But which way will nitrogen be moving? Into or out of the bottle? Yeah. Pressure out PN2 out here is 593. PN2 in the bottle, 500. So which way will nitrogen be moving? In. How about oxygen? PO2 out here is 160. PO2 in here, 200. Out. CO2? 0.3, 60. Out.
really fast?
Yeah, CO2 will have a pretty strong tendency to move. Actually, all of them will. In fact, nitrogen will have the strongest tendency, biggest delta P.
My kids are obsessed with the fact that if you open a can in space, it doesn't do anything. Like if you're in there's no bubble, there's no sound. It just opens and then they.
Because we're imagining we're in the vacuum of space
Right.
and we have a can of Coke or something.
Yeah.
I mean, it won't make a sound because there's no sound in space.
Right. There's still bubbles, but it doesn't do the same.
And let's ignore the whole freezing thing. It'll definitely bubble. As to the psst, when you open the can, I'm thinking it would, although you wouldn't hear it. It'd still be outgassing. Let's actually talk about it. Why do sodas bubble? Carbonation, but let's see what that means. Actually, before we do that, we have to talk about partial pressure in solution. So, but it's a good thing. We will come back to it. It's a good topic. Okay, so we now understand partial pressures in a gas mixture, I hope. So now it's going to get a little bit weird. Gases can dissolve in liquids. But when they do, they don't change the pressure of the liquid. And yet, we have to be able to talk about the partial pressure in solution. So things get a little strange here. Let's imagine that we have a bucket of water. Let's say that there is no oxygen dissolved in this water. We start out with water totally devoid of dissolved oxygen. We're going to put it in a room where the PO2 is 100 millimeters of mercury. So I've got oxygen molecules up here bouncing around, none in the water. Now, it's possible for oxygen molecules to move into the water. If one bounces into the surface in the right way, it can get in between the water molecules and become dissolved in the water. So, right at first, since there's no oxygen in the water, I'm going to say that the rate at which oxygen is entering the water will be greater than the rate at which it's leaving, since the rate at which it's leaving should be 0, since there isn't any in there. We agree? So the rate at which it's entering the water is greater than the rate at which it's leaving. So we start to observe oxygens in the water. Now, it is very tempting to think that oxygen will move into this water until the concentration of oxygen here is the same as the concentration here. In other words, if I draw the little dots, they'll be the same density. But that is not what's going to happen. Gases in liquids don't behave like they do out of liquids. I have found the easiest way to think of it is that gases have a certain amount of time on average they're willing to stay in a liquid, which is different for different combinations of gas and liquid. Oxygen does not stay very easily in water. Think of it like water's the hotel and oxygen is a very lucky guest. Only stays for one night, usually. So, as soon as some oxygen comes in here, the rate at which oxygen is leaving the water starts to go up pretty fast because that oxygen doesn't stick well. It comes out easily. So it starts rising quickly. Now, looking at this, is oxygen entering or leaving the water faster? Entering. So over time, we end up with a little more, but that increases the rate at which it's leaving. In fact, if I put 3 on there, it's probably going to be like this. At this point, oxygen is entering and leaving the water at the same rate. So what happens to the amount of oxygen in the water over time? It becomes constant, right? If it's entering and leaving at the same rate, that's the amount we will see. We're at equilibrium. What's the pressure of oxygen in this water? That's the question we're going to ask. Now, if this were a gas mixture, and we said it's moving this way and that way at equal rates, what would be the partial pressure of oxygen? Why 50? It's in equilibrium with 100.
Oh, it's at
What must it be here?
0?
It should be 100 to be in equilibrium. That's the only way these two gases would be in equilibrium. However, this is not the same concentration of oxygen as it is here. And yet it's at equilibrium. So we say that the partial pressure of oxygen in this water is 100. We probably say the partial pressure of oxygen in solution is 100. Now note, that does not mean the concentrations are the same, does not mean the amount of oxygen is the same. It just means that oxygen is in equilibrium with the gas at 100. The oxygen in here is not exerting any significant pressure on the walls of the bucket. There's not another 100 millimeters of mercury pushing out on it. The easiest way to think of it is that it's the pressure of oxygen trying to get out of the water. And with this gas mixture out here, oxygen will come in until it's trying to get out with the equivalent of 100 millimeters of mercury of pressure. Does that make any sense? Didn't think so, okay. Partial pressure in solution is tricky. Hot tub. People.
Okay.
Okay. People out here partying. This is the gesture I do to indicate partying. I don't go to many parties. So, they are exerting a certain amount of pressure on the walls of the room in which they are found. We're going to say they're exerting 100 millimeters of mercury of pressure on the walls. Good? Everyone okay with that part? Now, someone opens the hot tub. It's a very deep hot tub. Okay. People start getting in the hot tub. The hot tub's real hot. People don't want to stay in the hot tub very long. So, let's say we've got a fairly high density of people out here. And a few people jump into the hot tub.
No diving.
But this is a very hot tub, so people don't want to stay in here very long. And we get to the point where people are climbing out of the hot tub at the same rate that they're going in. Okay? We get to that point when there's, say, 2 people in the hot tub at any point. So we'll give this one a stupid name. It's that kind of party. Okay. So, we reach the point at which people are climbing out of the hot tub at the same rate that they're jumping in. So, if people out here are exerting 100 millimeters of mercury of pressure, and they're at equilibrium with the tub, what's the pressure of people coming out of the tub? The equivalent of 100. If it were less than that, people would still be coming into the tub. If it were greater, they'd be coming out faster than they were going in. Does that make sense? A little bit? Everyone at least willing to go with it? So let's say that we have some secret underground tunnel and we add a few more people to this hot tub. Now there's 4 people in the hot tub. People start coming out faster than they're going in. People come out of the hot tub at a certain rate. If I add more people, they're coming out faster. What I did was increase the P people of this water. And so people came out until the P people, which sounds bad. They're not peeing in the hot tub. Although we could probably extend the amount, never mind. So, the idea is that when these are in equilibrium, we say the partial pressure of the gas in solution is equal to the partial pressure of the gas outside, even though the partial pressure in solution is not exactly a pressure.
Can you see the one sentence again? You said that when they're at equilibrium.
So when the gas dissolved in the liquid is at equilibrium with the gas above the liquid, outside the liquid, then we say that the partial pressure of that gas in solution is equal to the partial pressure of the gas outside.
Is that
Good.
Is this 100 a definite number, or is that just depending on?
I made that one up.
Okay. And is this just for water, or is it for any liquid?
Any liquid, although the amount that would be at equilibrium in a different liquid might not be the same. I'll get to that in a second.
Okay.
So let's just do this. What if we turn on a valve and add oxygen to this room? So now it's 200. This would be like a bunch more people arrive at the party. So, are these still in equilibrium? No. Now the tendency to go in is much greater. So more oxygen starts to accumulate until the tendency to come out is greater. What's the PO2 in here in solution once they're at equilibrium? 200. Very good. Likewise, if more people come, you'll get a few more people jumping in before the rate at which they go in and out is equal. So the P people will not be higher. That could be, but let's not extend the analogy that far. Okay, everyone sort of okay with the idea of partial pressure in solution?
a question. How do you mathematically get the values for the ones on top for the pressure, atmospheric pressure, and then the 5
This
and such?
I give you. That's just about what it is.
Yeah, but the other numbers are still 5
These?
3, yeah.
This is total pressure times percentage nitrogen. The partial pressure of a gas in a mixture is the total pressure of the mixture times the percentage of that gas.
So you times it by 0.7.
And then, just to add on to her question, how did you get the answer for the CO2 one? Because I actually want to see if you figured that one out.
This is 760 times 0.0004.
Why?
Just this is a
It
I know
is.
something, yeah, I know something to the question.
No, it's not. It's okay.
because this is also
78% is 0.7. 0.04%.
So
Yeah.
what's this from? Oh, is that?
All right, how are we on that? Are we all good? You ready to take it one step further? Yes, of course you are. Yeah.
This is
That's pretty good. All right. Here's the problem. There's several things that affect these numbers. So if I say, here's 200 milliliters of mercury of oxygen, we let it dissolve until it's at equilibrium. And I can say, now this much oxygen in that water is the equivalent of 200 milliliters of mercury. That depends on several things. The temperature, for example. If I heat up the water, the rate at which the oxygen leaves increases. So the PO2 of this is dependent on the temperature of the water. If I lower the temperature of the water, if I make it colder, more oxygen will be able to come in before it reaches equilibrium. If I heat it up, oxygen will leave. So, cold liquids hold more dissolved gases. This has a huge impact in terms of marine biology. Cold water holds more oxygen. It can support a greater diversity of life. One of the reasons why the Central California coast is so rich in interesting marine life. Cold water coming up from Monterey Canyon and things like that, bringing oxygen-rich, nutrient-rich water.
Freezing.
Hmm?
It's freezing.
Oh yeah, and it means when you go swimming, you need a wetsuit or even a dry suit. Yeah, anyway, here's another interesting part. It's not the same for every gas. Let's put in over here. Carbon dioxide at the same partial pressure. So, which way is it going to go? Into or out of the water? In. Good. And so CO2 starts entering the water. Now here's the thing. CO2 sits more easily in water than oxygen does. Why? There are reasons, don't worry about them right now. So, as CO2 starts accumulating, it starts leaving, but not as quickly, not as fast. So we can build up more CO2 before it's leaving at the same rate. What's the PCO2 in this liquid?
200.
By definition, if it's at equilibrium with this, it must be 200. Is the water holding more CO2 or more oxygen? More CO2. Even though they have the same partial pressure, CO2 dissolves more easily in water than oxygen does. So at the same partial pressure, you actually have more of the CO2. That's one of the weird parts about CO2, about partial pressure in solution.
So remember,
I would like you to remember actually that CO2 has a higher solubility in water than oxygen does. That's a good thing to remember. Actually, oxygen is not very soluble in water. Oxygen solubility in water is pretty poor, which is one of the reasons why humans can't have gills easily. There's just not enough oxygen in that water for you to support yourself unless you had gills 100 feet long. Whales breathe air. But there are large sea creatures, for example, near and dear to my heart, giant squid and giant octopus, large creatures. Giant octopus get tired really fast because their blood just can't carry enough oxygen out of that seawater. There's some evidence that giant squid may be relatively passive at death. We've seen them very rarely at death. So, it is mostly the same. Deep levels are colder, but there are complicated things going on there with things using the oxygen and how quickly the oxygen can get into deep water. So how much oxygen is present in deep ocean water is not a simple question. Sorry? A lot of factors in that. Okay, take 5.